Monoidal categories and their representations, Lecture 18, Projective Bimodules. Let us start with the setup. Let K be an algebraically closed field, and let A be a finite-dimensional K algebra. We assume that A is basic. This means that all simple modules of A are one-dimensional. We also assume that A is connected. This means that A is not a direct sum of two non-zero subalgebras. And we also assume that A is self-injective. This means that all projective A modules are injective. In particular, with all these assumptions, we have that A is the quotient of the path algebra of a connected quiver by an ideal I, which is contained in the square of the arrow ideal of this quiver. And since we assume that A is finite-dimensional, we also automatically have that our ideal I contains some power of the arrow ideal. In other words, I is admissible. Now let us define the monoidal category of projective AA bimodules. To start with, we have the monoidal category of all finite-dimensional AA bimodules. We denote by CA the additive closure in this category of all finite-dimensional AA bimodules of two objects. The first object is the regular AA bimodule A, and the second object is the projective AA bimodule A tensor over K A. Note that if we take the later object, A tensor over Ka, and tensor it over A with itself, then here in the middle we will have A tensor over AA, which is just A, and this is a multiplicity vector space for the outcome. So the outcome is A tensor over Ka with the multiplicity given by the dimension of A. And of course, tensoring with the regular bimodule does nothing because the regular bimodule is the identity object in the category of all AA bimodules. This implies that our additive category CA is in fact a monoidal subcategory in the category of all AA bimodules and in the category of all finite-dimensional AA bimodules. We will call CA the monoidal category of all projective AA bimodules. However, strictly speaking, the projective AA bimodules are the bimodules in the additive closure of A tensor over Ka. We have to add the regular bimodule A because we need an identity object in a monoidal category. But this bimodule does not have to be projective. Sometimes it is, sometimes it is not. And also note that the regular bimodule is indecomposable since we assume that A is a connected algebra. Now let us describe indecomposable projective AA bimodules. We fix a primitive decomposition of the identity in A into a sum of primitive idempotency, E1, E2, and so on, En. So each EI is a primitive idempotent, and they are pairwise orthogonal. If we multiply different EI and Ej, we get 0. Then the indecomposable projective AA bimodules are exactly the AA bimodules of the form AEI tensor over K with EJA. So here I and J are indices between 1 and n. And then we have the following multiplication formula for these bimodules. If we take AEI tensor over K EJA, and tensor over A with AES, tensor over K ETA, we will get the bimodule AEI, tensor over K ETA. So the left-hand side comes from here, the right-hand side comes from here. And then we have the multiplicity vector space here in the middle, which is exactly EJAES. So we will have this bimodule with a direct sum multiplicity given by the dimension of the space EJAES. Note that in principle, this dimension can be 0. The space EJAES can be the 0 vector space. However, if J is equal to S, then EJ contains EJ. So in this case, the space is always non-zero, and so this multiplicity is non-zero. Let us first briefly discuss the semi-simple case. If we assume that A is semi-simple, then A is isomorphic to K, because it's a semi-simple connected algebra over an algebraically closed field. In this case, the regular bimodule A is actually isomorphic to the projective bimodule A tensor over Ka, because everything here is K. Consequently, the monoidal category Ca is actually equivalent to the monoidal category of all finite dimensional K vector spaces. And we know that the latter category has unique simple transitive module category, and this module category is just the regular module, so the regular action of this monoidal category on itself. More generally, algebra objects in K-mod are exactly the finite dimensional K algebras, and since K-mod is a rigid category, due to the theorem of Ostrich, we get that any finitary representation of K-mod is given by the natural action of K-mod on B-proj, where B is a finite dimensional K algebra. So this completes the semi-simple case, and therefore from now on we assume that A is not a semi-simple algebra. Next, let us describe the cells of the monoidal category Ca. For brevity, let us denote by Qij the AA bimodule AEI tensor over K EJ A. Note that for any ij and s, tensoring Qij over A with Qjs gives Qis with a multiplicity given by the dimension of EJ EJ. And as we already mentioned, this dimension is non-zero. In particular, then, from this formula, we see that starting from Qjs, we can multiply it on the left with something to get Qis with a non-zero multiplicity. This means that Qis is left greater than or equal to Qjs. And of course, it's clear that every indecomposable bimodule is left greater than or equal to the regular bimodule, because the regular bimodule is the identity object. And then this implies that the left cells of Ca are as follows. We have the left cell given by the regular bimodule. It contains only one indecomposable object. And then for any j between 1 and n, we have the left cell consisting of all Qij where I varies between 1 and n. So we have n plus 1 different left cells. Similarly, we have n plus 1 different right cells, the special one given by the identity object, and then for any I, the left cell consisting of all Qijs where j varies between 1 and n. And we have two two-sided cells, the one given by the identity object and the second one containing all Qijs. So this is a big difference with the semi-simple case, because in the semi-simple case we only have one two-sided cell. Okay, let us also do one very explicit example. Consider the following quiver with two vertices 1 and 2, an arrow A from 1 to 2 and an arrow B from 2 to 1. And let us denote by R the quotient of the path algebra of this quiver modulo the relations ABA is equal to 0 and BAB is equal to 0. As primitive idempotents, we can take the trivial passes in each point. So we have E1 and E2. E1 is a trivial pass in 1, and E2 is a trivial pass at 2. So if we denote the simple modules corresponding to the vertices by L1 and L2, and also for brevity, we just write the bold I, where I is 1 or 2, to denote these modules, then we have the following Loewi diagrams of the indecomposable projective modules P1 and P2. So P1 has top 1, then using the action of A, we can go to the middle term 2, and using the action of B, we can go to the socle 1. And P2 has top 1. Applying B, we go to the middle term 1, and applying A, we go to the socle 2. So both P1 and P2 have simple socles, and then it's easy to check they are also injective. So it's a typical example of our setup. Now let us look at the picture of the indecomposable bimodules. So let us denote by ij the simple top of the indecomposable projective bimodule R ei tensor over k ej r. So here I and j are 1 or 2. So then we have the following picture for the identity bimodule. So the left regular module R is P1 plus P2. But now, if we also consider the right action, as a bimodule, it becomes indecomposable. So this is a copy of P1, 1, 1, 2, 1, and 1, 1. So this is the left module P1, and this is the left module P2. And now the right action changes the second index. So starting from 1, 1, using the left action, we can go to 2, 1, and then to 1, 1 again. But using the right action, we can change the right index to go to 1, 2, and then to 1, 1. Similarly, starting from 2, 2, using the left action, we can go to 1, 2, and then to 2. And using the right action, we can go from 2, 2 to this 2, 1, and then to this 2, 2. From the point of view of the basis of our algebra, this corresponds to E1, this corresponds to E2. This element is A, this element is B, then this element is BA, and this element is AB. The projective indecomposable bimodule R EI tensor over K EJR looks as follows. So here we denote by S overlined the complement to S in the set 1, 2. So the top element is IJ. Using the left action, we can change the I to I overlined to its complement, and the J remains the same. And again, using the left action, we can go to IJ. Again, we change I overlined to I. Using the left action from the original IJ, we can go to IJ overlined, and then again to IJ. And so the connections here, lines which go to the left, they represent the left action. The lines which go to the right, they represent the right action. And so the dimension of this bimodule is 9, because this is a 3-dimensional module, this is a 3-dimensional module, and this is just such a square of dimension 9. Okay, now we can also very concretely describe the cells in this example. So we have the minimal left, right, and two-sided cell consisting of the regular bimodule R. And then we have the maximal two-sided cell, which contains the 4 indecomposable projective bimodules. This is Q11, this is Q21, Q12, and Q22. So here the columns are left cells. So when we change the left index, we can change the left index using the left multiplication. So this is a left cell, and rows are right cells. We can change the right index using the right multiplication. So we have 3 left cells, 3 right cells, and 2 two-sided cells. And we can explicitly write down the table of multiplication for projective bimodules. So if we tensor one projective bimodule with the other one, what we should do, so the left part of the outcome comes from the left part of the left vector. The right part of the outcome comes from the right part of the right vector. And then we have a possible multiplicity given by the dimension of the middle part. So in particular, RE1 tensor E1R. If we now tensor it over R with RE1 tensor over K E1R, we will get RE1, this comes from here, tensor over K E1R, this comes from here. And the multiplicity is the dimension of E1 RE1. So since the projective module RE1 has 2 simple subquotients isomorphic to L1, the corresponding multiplicity here will be 2. And now, if we tensor RE1 tensor over K E1R, if we tensor this over R with RE2 tensor over K E1R. Then we will have RE1 from the left factor, E1R from the second factor, but now the multiplicity vector space is given by E1 R E2. So since the projective P2 has only one simple subquotient isomorphic to L1, the corresponding space is one-dimensional, and so the multiplicity here is 1. And similarly, one can compute all other tensor products. So this is the multiplication table of indecomposable projective bimodules. We claim that under our assumptions, the category Ca is rigid. In other words, it has adjunction morphisms. Proof. In order to prove this, we need to show that the object AEI tensor over K EJA, that this indecomposable projective bimodule, has a right adjoint in Ca. If we consider the corresponding endofunctor of A mod given by tensoring with this indecomposable projective bimodule, this functor is exact because EJA is projective as a right module. And since this functor is exact, it does have a right adjoint. And the right adjoint is given by homing over A from this bimodule to somewhere. Note that this functor, homing over A from this bimodule to somewhere, is also an exact functor because AEI is projective as a left module now. And since it is exact, it is isomorphic to the functor of tensoring with a certain AA bimodule, namely with a bimodule which you get if you plug in here the regular bimodule A in the second place. So this means that we need to understand the AA bimodule home over left A action from AEI tensor over K EJA to A. So now we need to understand this AA bimodule. Using the tensor home adjunction, so we cut this in the middle, and in the tensor product with AEI, we move AEI to the second variable. So this AA bimodule is therefore isomorphic to the AA bimodule given by home over K. So here we have the K action, EJA, comma, home over A from AEI to A. Now we recall that home over A from AEI to A is just isomorphic as a vector space to EIA. And this isomorphism is given by sending a homomorphism phi from the left-hand side to its evaluation at the generator EI of this indecomposable projective module. And then we end up in the right-hand side. So therefore, this displayed formula can now be simplified to home over K from EJA to EIA. And now here in the second component is projective over K for obvious reasons because K is a field. And since it is projective, we can move it out of home and just leave our K in the second place. So home over K from EJA to EIA is isomorphic to home over K from EJA to K, tensor over K with EIA. So now, as a first component here, we have the dual to the projective module EJA. So a dual to a projective module is, of course, injective by definition. Therefore, we have an injective A module, but we assume that A is self-injective, so any injective A module is projective. So this means that home over K from EJA to K must be isomorphic to some AES for some S. And therefore, this means that we have the adjunction morphism between the tensoring with the original bimodule AEI tensor over K EJA and tensoring with the bimodule which we got from this computation, which is AES tensor over K EIA. And this adjunction morphisms between two functors lifts from endofunctors of A mod to CA, because natural transformations between functors are simply given by homomorphisms between the corresponding bimodules. And this establishes the rigidity of CA. Now let us discuss cell modules over CA. Consider first the left cell given by the regular AA bimodule A. So this left cell just consists of the identity object. All other objects are obviously left greater than or equal to the identity object. So to determine the corresponding cell module CL, we need to take the quotient of the regular CA module by the unique maximal CA stable ideal in the regular module. Of course, all projective bimodules inside the regular module must be in that unique maximal ideal because they are strictly left greater than the regular bimodule A. This should be greater. So this means that all projective bimodules will actually act as zero on the cell module which corresponds to our left cell L. And also the radical of the endomorphism algebra of the AA bimodule A must be in that maximal ideal, because when we forget the projective bimodules, the only thing which is left is the identity object. And the identity object always acts as the identity functor up to isomorphism. And the identity functor always preserves the radical of the category. So it follows that the underlying category of our cell module is just K mod. We have one indecomposable object and there is no radical of its endomorphism ring. So this is K mod. Alternatively, we can describe this by the fact that if we kill first all projective bimodules and then the radical of the endomorphism ring of the identity, then we construct a quotient of our monoidal category CA, which is equivalent monoidally to the category of K vector spaces. And that has a unique simple transitive representation, the regular one, and that simple transitive representation is exactly our cell module corresponding to the first cell L. Next, let us discuss the natural CA module. We have the obvious action of AA bimodules on A modules. So if we have a left A module, we can tensor it on the left with an AA bimodule. We can restrict this action from all AA bimodules to CA, which is a monoidal subcategory of all finite dimensional AA bimodules. So this means that we have a natural action of CA on A mod. So this module is usually called the natural CA module. Let us observe that if Q is a projective AA bimodule, then for any A module M, the tensor product of Q and M is projective as an A module. This means that the action of CA on all A modules can be restricted to an action of CA on all projective A modules. They are, of course, stable under the action of the identity, but we just said that projective AA bimodules send everything to projective modules. So the action of CA on all A modules restricts to the action on all projective A modules. In other words, the natural action of CA on all projective A modules is actually a submodule of the natural CA module. Please note that the natural action of all AA bimodules, or all finite dimensional AA bimodules, on all finite dimensional left A modules does not restrict to an action on all finite dimensional projective A modules. If we have a weird AA bimodule, we can apply it to a projective A module and get something which is not projective. So here, for this to work, we really need to look at the category of all projective AA bimodules. Now we can discuss all other cell modules. So let us fix an index j between 1 and n and consider the corresponding left cell Lj, which consists of all Qij's where I is between 1 and n. This cell is a maximal equivalence class with respect to the left order. Therefore, if we look at the regular CA module, the regular action of CA on itself, we can restrict this action to an action of CA on the additive closure of the elements in Lj inside CA. So let's denote the latter action by bold N. So this is the action of CA on the additive closure of the elements inside Lj, and everything happens inside the regular CA bimodule. So in order to construct the cell module, we need to factor out from N the unique maximal CA stable ideal. Let's denote it by bold I. It is easy to check that homomorphisms as AA bimodules from the indecomposable AA bimodule AEX tensor over K EYA to the indecomposable AA bimodule AEU tensor over K EVA is isomorphic to EXAEU tensor over K EVAEY. And note that the left action of CA cannot affect the right component EVAEY, because the action on the left only affects this left component. We have this tensor product over K, which disconnects the left component from the right component. So this implies that our maximal ideal bold I contains everything generated by the radical of the right component morphisms. For our left cell, when we fix J, so our right component is always EJA. So the right component endomorphism is the algebra EJA. And so our ideal I contains everything generated by the radical of the right component algebra EJA. Let us for the moment denote by I prime the CA stable ideal of N generated by this radical, by the radical of the right component algebra EJA. Then, if we look at this formula and we factor out here the radical of the algebra, what remains here is just K. This means exactly that home in the quotient of N by I prime between the same indecomposable objects now becomes EXAEU. This is because we have killed the right component. The radical is killed, the quotient by the radical becomes K, and K just disappears in this tensor product. So let us denote by Lx the simple top of the indecomposable projective module AEX. So here X is between 1 and n. By Yoneda lemma, there is a morphism phi from the regular CA module to the module given by the action of CA on A mod, which sends the identity object in the regular module to the simple object Lj. So this morphism phi then sends Qij to the action of Qij on Lj. And if we take Qij, which is AEI tensor over K EJA, and we tensor over A with Lj, so we will have here EJA tensor over A Lj. So this gives us EJ Lj, which is just K. So the outcome will be AEI. It is also quite easy to see that the radical of EJ Lej kills the module Lj, which means that our map phi factors through the quotient of n by I primed. And from the above computation, we see that the home space in this quotient, it is given exactly by this EXA EU, and in A mod, we will have just homes between the indecomposable projectives, which are given by the same formula, which means that the homomorphisms in A mod and in N modulo I prime, they just coincide. This implies that the action of CA on A proj is equivalent to the action of CA on the quotient of n by I prime. Note that we only know that I prime is contained in I can potentially be bigger. And we claim that this doesn't happen. In order to prove this, we first note that the action of CA on A projective modules is a simple transitive module. We will prove it on the next slide. As soon as we know that this is a simple transitive module, it doesn't have any quotients. If I prime would be strictly smaller than I, then factoring the difference out, we should be able to make a proper quotient of n divided by I prime. But this doesn't happen because this module is simple transitive, which implies that I is actually equal to I prime, and this then means that the cell module over CA, which corresponds to our left cell Lj, is equivalent to the CA module given by the action of CA on the category of projective A modules. Note that the latter one doesn't depend on J. So all CLJs are actually equivalent because they all coincide to this natural action of CA on projective A modules. Now we have to prove the lemma. The action of CA on A projectives is a simple transitive module. Okay, so the homomorphisms from the indecomposable projective A module AEX to an indecomposable projective A module AEI are given by the elements in the space EX A EY. So if we have such an element A, we can apply our projective AA bimodule A tensor over KA to this A, so by tensoring over A. The outcome will be the morphism 1 tensor over A, and this will be a morphism from our projective bimodule tensored over A with AEX to our projective bimodule tensored over A with AEY. Now we can contract A tensor over A and get a morphism 1 tensor A from A tensor over K AEX to A tensor over K AEY. And here, because it's tensor over K, AEX and AEY are just multiplicity vector spaces. So if our original homomorphism A were non-zero, then we would have here a non-zero map between these multiplicity vector spaces. So we can choose bases in these vector spaces such that this map maps a basis element to a basis element. And then projecting onto the corresponding direct summons, we would get the identity map on some indecomposable projective object. And consequently, the CA stable ideal generated by our non-zero map A must contain the identity map on some indecomposable object. And since the action of CA on A proj is obviously transitive, we automatically get that this ideal is the whole of A proj. So any non-zero homomorphism in our category generates the whole category as a C-stable ideal. And this completes the proof of our lemma. Let us illustrate this argument in our explicit example. So here is a picture of an indecomposable projective RR bimodule, which we had before, but now with the left action given by solid lines and with the right action given by dotted lines. And the part which belongs to our ideal I prime is given by the teal color, so it's here. So if we decompose our module as a direct sum of right modules, we will have exactly these three dotted lines. And then the radical is, of course, given by these parts. So this teal part is exactly the right radical. And if we factor it out, what remains is exactly one copy of the left indecomposable projective module. So the action on the left, it cannot change the right component, and this indecomposable projective left module is exactly what remains when we factor out the right radical from our indecomposable projective bimodule. So this is an illustration how the this thing works in the explicit example. Now we can formulate the result, which classifies simple transitive CA module. So the theorem, which is due to myself and Vanessa Mimitz from 2015, the above actions of CA on K mod and on approach are the only simple transitive CA modules. The reference to this result is our paper Transitive two representations of finitary two categories, which appeared in Transactions of the AMS in 2016. So in 2015 it was a preprint. Remark: the proof of this theorem crucially uses the Perron-Frobenius theorem. And another remark is actually one can prove a similar result in a more general setup when one removes the assumption on A to be self-injective. However, in this general setup, CA is no longer rigid. And then one needs to find a different argument. So the proof given here doesn't work in that more general setup, and one needs to develop many more machinery in order to be able to prove a similar result in this general case. So this is done in the paper of myself, Vanessa Mimitz, and Xiaoting Chang, which appeared in 2020 and which is called Pyramids and Two Representations. So in fact, this classification is valid without the self-injectivity assumption on A. Let us also briefly discuss Coalgebra objects for CA. The claim is that the indecomposable projective bimodule AEI tensor over KEIA has a natural structure of a Coalgebra object in CA. The counit map is given by the multiplication map from AEI tensor over KEIA to A. The comultiplication map from our indecomposable projective bimodule to its tensor square over A is given by the map which sends the generator EI tensor EI to EI tensor EI tensor EI tensor EI. This uniquely defines the map because this indecomposable projective bimodule is generated by EI tensor EI as a bimodule. So the coassociativity of the comultiplication is really obvious because we start from here, we go here, and then we apply the same map either here or here, we clearly end up in the same place. The counitality, one has to check on the diagram, and there one needs to use that EI is actually an idempotent. And then if we combine it with the fact that EI tensor EI generates the indecomposable bimodule, we get the counitality. Note that this works for any I. So here I can be arbitrary from 1 to n. And then we know that if we have a Coalgebra object, we can consider the category of all comodules for this object inside CA, and we know that this category is a CA module. Of course, the Coalgebra object itself is a comodule over itself, given by the structure map, so the coaction is given by comultiplication. And if we start from this object, and if we act by CA on the left, we obtain a certain category CA times C. And this category is a finitary module over CA. And the claim is that this finitary module is equivalent to the cell module, which corresponds to the left cell Li. The indecomposable C comodules in this category will be given exactly by the indecomposable objects AEX, tensor over K EI A. And the comodule structure here, the coaction of our Coalgebra C on this object is given by the following map. So we have our object, and we have to go to our object tensor over A with our Coalgebra. And this map starts from EX tensor EI, and it sends this generator to EX tensor EI tensor EI tensor EI. And then one can check that all axioms are satisfied. And then one additionally can check that the additive closure of these guys gives us the CA module, which is exactly the cell module which corresponds to the left cell of I. Okay, some problems and questions at the end. Question 1. Prove with all details that each QIS is left greater than or equal to the identity object A. Question 2. Prove with all details that hom over A from AEI to A is isomorphic to EIA. Question 3. Prove with all details that hom over K from EJA to EIA is isomorphic as an AA bimodule to the tensor product of the dual of EJA with EIA. Question 4. Prove with all details the hom formula that the hom in the category of all AA bimodules from AEX tensor EYA to AEU tensor EVA is isomorphic to EXAEU tensor with EVA EY. And question 5, check with all details that CAC is equivalent to the cell module CLI as CA modules. This refers to the previous slide. Thank you very much and see you next time.